So for this afternoon, when you look at the talk by Dr. Wang previously, he also mentioned some parts related to rank and crank. Because when we have the partition P5n plus 4 is congruent to 0 mod 5. So that's one example. It is interesting to see how to classify the partitions into 5 groups where each group has same number of elements. So we will see more details with Dr. Nankun. And I think, yeah, time is yours. So please.
Thanks Wuha for introduce and invite me to join this summer school on number theory and cryptography held at Universitas Gajah Mada. I hope I pronounce this right. Gajah Mada, okay. And I know Liu Quan gave a talk this morning, and before the talk, Wuha also provides something about partitions and involve something about the ranks. So I hope you got a good rest after Liu Quan's talk, and please feel chill to enjoy or what anything you want during the lecture. So this lecture is an introduction for ranks and cranks, because ranks and cranks is an important part for research part of the partitions. So in this talk, we will introduce the integer partitions first for the completeness of this slides. Although in other lectures, you have already know the definition and something about partitions. And then we will introduce the ranks and cranks of partitions. And we will compare 2 of these notations. And then we will introduce the works of Atkin and Swinnerton-Dyer's work. And then a general introduction about the recent works on ranks of partition. Then there's a conclusion. Okay, so first, let's see the definition of the integer partitions. This can be treated as a review of the previous lectures. So a partition function of positive integer n is a sequence of non-increasing positive integers which add up to n. We use the function Pn here to count the number of partitions of n, and we agree that P of 0 is 1. Okay, so we give a trivial example. For the P of 4, it equals to 5. We can count it this way. We can write 4 as the 4 itself, and also we can write 4 as 3 plus 1. And then another way is 2 plus 2, and then 2 plus 1 plus 1, and the last one is 1 plus 1 plus 1 and 1. So we have 4 different ways to represent the 4. So we got the Pn equals to 4. And here, armed with computer programming, one can verify that these 3 values. We can see that the value of Pn increase very quickly. For P of 100, you got such things. If you have ever watched the movie The Man Who Knew Infinity, you will see that the Professor McMahon and the Ramanujan got a bet to calculate a value of P, right? So if I didn't make mistakes, what we count is this one. And here we introduce the Young diagram, and it's also called fairy diagram. So if we use this kind of diagram to represent the partition, that means the number of the square in the same row represents a number add up to n. For example, here is 5. And the second row, we have 4 squares, and the last one have 1. So we got a 10. That means this is a way to partition the 10. So this is 1, 1 corresponding from the diagram to a partition of n. Okay. So let's see the generating function of Pn. I know you already have seen this many times, but let's see it again. It comes from Ola proved this generating function for Pn, and Pn here equals to this kind of things. And this, if we expand it, it looks like this. And really, we require that Q equals to e to the power of 2 pi times I times tau, with the tau as a complex number. And the image part of the tau is greater than 0. That means the complex number will lie on the upper half plane. And under this restriction, the abstract value or the module of Q will be less than 1. Okay, why we write Q like this? Because some view from the modular form, if we write things like this, it will give a lot of convenience, and when we calculate it, it will be much more easier, maybe. And in this lectures, sometimes I will give some comments, but the thing is, my comments might be not correct, so just listen, okay? And how to see the generating function, how to prove it, will give a very trivial idea. If we look at every fraction here, we can write this thing as a summation of the infinity series like this. If we write 1 over 1 minus q, we can got this. It's a series, and for 1 over 1 minus q square, it can be right like this. And for the 1 over 1 minus q cubic, it can be expanded as this. So how to say the coming of the generating function? Let's see. Again, we use P of 4 as an example. We already know 4 has 5 different ways to partition it. So we will get a corresponding between the series and the exact partition. For example, if we want to represent the 4 here, we can see from here first. If you want to grid the P of n, what you have to do is to get the n, qn here. For example, if you want to get Pn, so what you have to do is to just open or expand all the series here to get all the things together. For example, if you want to get P of 4, right? You can just times all the series here and find the coefficients of the Q of 4. So for the 4 here, how to get the coefficient 1 from the series, it comes from this. This equals to 1 over 1 minus q to the power of 4. And for 3 plus 1, the 3 can come from here, the q cubic. And another one can come here. This comes from 1 over 1 minus q, and this comes from 1 over 1 minus q cubed to the power of 3. So you get the basic idea is that if you want to represent a number directly, you just find the key 1 over 1 minus q to the power key and expand it and find the power here. But for the same number here, for example, here 2 of 2. So it's another way to count it. We use 1 over 1 minus q square, and q square times q square, we get q to the power of 4. It corresponding to this. So the production of q square with q square transferred to 2 plus 2. So in this way, for this 2 plus 1 plus 1, we got 2 of the exponent of q comes here for the 2. And here 2 of 1, so it comes here. Cubic comes from q times q. And for the last one, we got q times q times q, and times q got q to the power of 4. So that's all the way we can get q to the power of 4 from the series. So this is the idea of how to get a generating function. And later, for the generating function of rank, we will see it again. Okay, so let's see the Dedekind eta function. It's a very useful function and important function, and it's also a weakly modular form. Let's see the definition of it. So for the same condition here, we ask the q to be the e to the power of 2 times pi times I and times the tau. And the imaginary part of the tau should be greater than 0. Okay, so we can write the generating function here as this. So this is the Dedekind eta function. And the Dedekind eta function is a weakly modular form of weight half, 1 of half. So maybe Liu Quan has mentioned this in morning's talk. And that means we have this condition. In fact, here we can write this part as this. So this part is called the weight of the weakly modular form. And here the data of ABCD should be a primitive 24th root of unity. And this ABCD for this part comes from a modular group, special linear group of Z with the 2 here. Okay, we just mentioned this eta function, but this is not the important part of our lecture, so we just skip it. And then let's see the asymptotic and exact formulas of the PA. It's very natural to think the formulas for the counting functions, because if we want to calculate P of n, we cannot use this generating function always, because once the n is big enough, we cannot count it by hand. Even we have a computer now, if the n is tremendous. We have to use a lot of time to get the answer. So we always want to get the exact formula for the PA. Okay. So applying the circle method, Hadi and Ramanujan obtain this asymptotic formulas n goes to infinity. And modifying Hadi and Ramanujan's method, Rademacher proved this exact formula. And when he he got this idea when he prepared the lecture notes for the students. And if you watch the movie I just mentioned, the manual Who Knew Infinity, Ramanujan got this, and he was selected as a member of the academy because he's this result. Okay, and in fact, the interesting here is that the basic tool here to prove this is just use complex analysis. You don't need much advanced tool. You just need complex analysis, and for more details, what you need is just a residual theorem, okay, and the Cauchy integral, okay, and in fact, it's a very beautiful proof to get this. So if you want to go to see a complete proof, you don't need to read the original paper. You can see the chapter 5 of this book written by Abstol, modular functions and the Dirichlet series in number theory. I remember that when I was PhD candidate in non-technological university, Wuhan, and I spent a lot of time on this book. Right? We had a 2-person seminar every week, and everyone to read a whole chapter and give a talk to other. And at that time, we just read the proof. And this book is a very good book. It introduced some basic fundamental thing about the modular form. So if you are interested to this kind of thing, I recommend you to read this book. Okay. Okay. So let's see the 3 famous congruences found by Ramanujan. And I have to say that all the legend about the partitions or stories may start from these 3 congruences. It generates a lot of things, and we can see that all the research article about the congruences of partition and the things about ranks and cranks may origin from this kind of thing. These 3 congruences. Okay, I believe that you have seen this many times. And after this, let's see more results on congruences for P of A. So first, the Watson established congruences for PA modular powers of 5 and 7. Okay, so we can see that from the original congruences modular 5, 7, and 11, Watson generalized this to the powers of 5 and 7. Okay, and then Atkin established congruences for P of A modular powers of 11. Okay, and there also exists congruences for P of A modulo other primes. So first, the result, we can see that acting at all brain proved this kind of thing. Okay, so the modulus here become 13, and in fact we can write this number as this kind of thing. So in fact, we can see that although there is a congruence of PA modular difference number, but it's not as beautiful as the original congruences here. Okay. And there's another result. We devised an algorithm and found many more explicit congruences for PA modular primes, less or equal than 31. Okay. And in fact, here are more results on this kind of things. Here, Kono in 2000 proved that for any primes L greater or equal than 5, there exist infinity many congruences of the type. So in fact, it's a very, how to say, very important, and this result is out of imagination, at least for me. And Ono use modular form as tools to prove this kind of things. So if you are interested in this kind of thing, like partition and ranks, you have to know the Q-series skill very well, and you can also learn some modular form, especially the weak modular form theory, weakly modular form, or mock modular form, not modular form. And Kono has a book write about this kind of things, the web of modularity. If you are interested in this, you can just read this. Read the book, the web of modularity. Okay, and then Uda proved that for any primes L greater or equal than 5, if we have this kind of congruence, then L A must be divided by L, and here these two Legendre symbols cannot be seen. Okay. So for the congruences of partition, it just maybe end there, or not there, sorry. And for these two mathematicians, they proved that for prime L, if there exists this kind of congruences for all n with some fixed beta, then L can only be 5, 7, and 11. So the difference with the previous results, modulo 3 or modulo 13, is here the L and the coefficients of n here are the same. That's why the original 3 congruences are such beautiful. Okay, so he gives a condition for the existence of this kind of congruence. So from this result, you will see that the Ramanujan found the only 3 such kind of congruences for P of A. It's a very amazing thing. Okay, and what impressed me more is that he got this result when he prayed. I hope that I can got this ability. So if we just have this ability, we just learn math and pray every day, and I believe that we can get more and more paper. But the thing is, there is only one Ramanujan. I just such a common person. What we have to do is work hard and read more and more paper. Okay. And later, Ruda proved that for L equals to 2 and 3, and there's two integers a and b such that a is greater than b and b is greater or equal than 0, then there exists a non-negative integer a naught such that this. So Ruda proved another kind of thing, that for some conditions, there cannot be such congruences. So in fact, it's an interest topic for me, because all the previous work tried to find the congruences, but he proved that for some conditions there cannot be congruences. Okay, so there is a short story about congruences of PFA. Okay, let's see the ranks and cranks. Okay, so what is ranks? Ranks of partitions provide combinatorial interpretations for Ramanujan's congruences for PA modulo 5 and 7. So there are 3 congruences, and the ranks can provide combinatorial interpretations for 5 and 7. Okay, so first, Dyson defined the rank of a partition in 1944. If I don't make mistake, Dyson got such things when he was a high school student or middle school student, I'm not sure, before he went to university. And we know that Dyson is a physician and also a mathematician. He has a very famous paper talk about mathematicians, the birds and frogs. Maybe you can read this article. It's not an academic thing, academic research paper. It's just something like a view of Dyson to see the mathematicians. He divides the mathematicians into 2 kinds. One kind is bird, one kind is frogs. It's a very interesting paper. Okay, so let's see the definition of the rank of a partition. It finds us, we use the largest part. For example, if we have a partition here, use Young diagram, the largest part is here, 4. And to minus the number of the parts. So here is a number of parts, is 2. So the rank of this partition is 4 minus 2 equals 2. Okay. Here is another example. This picture comes from the Wikipedia. And here for this part, if there is a partition of 3 plus 4 plus 3, or 6 plus 4 plus 3 plus 1, then the rank equals to the largest part, 6 here. And here we have 4 parts, 1, 2, 3, 4. So here minus 4, what we got is 2 here. And if we see this from the picture, we see that the rank in fact is this part. Okay, we find a square of triangle with 2 equal sides here and the more part here. In fact, it's a number of it's value of the rank. The number of the square here is a value of the rank. Okay. And here we use n of m and a, big N of M and N to denote the number of partitions of N with rank M. So here is another counting function. Okay. And here we use another notations, big N of M as N, to denote the number of partitions of N whose rank is congruent to M modulo S. Okay, so it write like this. You can see that the J is congruent to M modulo S, and we collect all the thing together. Then we got this. Okay. Here we give an example. Again, we use this. There's 5 partitions of the 4. So first, the partition is 4 itself. So the largest part is 4. And there is one number, right? So the number of parts is 1. So we get a rank of 3. And the rank of the 3 plus 1, we can also write like this, is the largest number, 3 here, minus number of parts here, 2. We got 1. Okay, so we got the rank of this equals to 0, the rank of this equals to minus 1, and the rank of this partition equals to minus 3. So if we use this symbol or use this notation, we got N of minus 3 and 4 equals to 1, because here is just one partition here with the rank minus 3, so it's 1. But let's see this, N of 2 and 5 and 4 is also 1, because this means the rank of 4 modulo 5 congruent to 2. Here we can find that should be wait, which one? Modulo 5 is congruent to 2. Oh, also this one. This minus 3 congruent to 2 modulo 5. Also only one of this. So here we got 1. Okay. So after writing the definition of rank, Dyson gave a conjecture that here, N of M and 5 and 5 N plus 4, that means the partition of 5 N plus 4 and the rank modulo 5 congruent to M. For all the M here, 1, 2, 3, 4, it should have this identity. That means N 0, sorry, N of 0, 5, and 5N plus 4 equals to N of this equals to this. Oh, sorry, and this, and this. And we have noticed that the thing is, if we get this, if we collect them all, what we get is P of 5N plus 4, right? Since all the partitions satisfy these conditions, if we collect them all, we get all the partitions whose summation is 5N plus 4. So we can see that if we got this, we will have the Dyson's conjecture from this view, from this V. That's why we call the ranks give a combinatorial interpretation of the congruences, because all the numbers here are same. I mean, all the functions n of this number here are same. So it interpretation this p of 5n plus 4 from the combinatorics. Okay, and the same for these congruences. And same as there's another open problem from this kind of thing, that is, for if you try to use let's say Young diagram, try to prove this kind of thing from the graph. No one have did it. No one have proved it. We just use Q series to prove this kind of thing, but no one have proved it by some very combinatorial way. How to say that? It's like use Young diagram. Maybe if you find a partition with rank congruent to S modulo 5 of here 5 modulo 5, and then from this you can generate another rank. Oh, sorry, this is rank maybe from 0. This rank, no, 1, 2, 3, 4, here from 2. For example, I mean, if we find a Young diagram here, the rank is 2 congruent to, the rank congruent to 2 modulo 5, right? And then you can from this diagram to generate another diagram with the rank congruent to 3 modulo 5. Then you can from this to generate a diagram with rank modulo 4 or modulo 5 congruent to 4, and then you got another rank with the rank congruent to 0 modulo 5, and then at last you got another diagram with the rank modulo 5 congruent to 1. And if you can find a proof this way, you can generate all the different ranks from 1 to 1 by 1, then you will give a new proof this. You can try to find it. And for this two conjecture, Atkin and Swinnerton-Dyer proved it in 1948 or 54, sorry. And I have to say that the mathematician Swinnerton-Dyer, you may heard about a very famous conjecture, the BSD conjecture. And in fact, the SD is for this mathematician. It's not two guys, it's just one person, okay? The BSD conjecture. Okay, let's see the generating function of ranks. The generating functions of n of m and n is given by this. And here I use notations in our directions here. The notations defined like this. The circle bracket is just an infinity product of these such things. So if you can, it's good if you can remember the exact definition of such things. Or if you think is that stranger to you, you're not familiar with this, you can just remember that the bracket is just a product. Okay, it's just a product. And if we say infinity symbol here, it's just an infinity symbol. If we see an n here, it will be a finite product. Okay. So we can say, in fact, this kind of thing is very similar to the generating function of P of n. So let's give a short proof or idea how to see the generating function here. We use the Young diagram again. So for the q to the power of n squared, in fact, it comes from the largest square we can find in the Young diagram. For example, if we have a Young diagram here, 1 plus 2 plus 1, the biggest square is here, okay? And if we have such Young graph, the biggest square is here, okay? So this part comes from here. And then we can say that the left side part of this, the left part of, sorry, the right part of the square, the right hand part here can treat as a partition, right? And the partition, the largest part is less or equal than the n here, right? Since what we found, the largest square has a side of n. So if we treat the right-hand part here as partition, that will give us restrictions. Give a restriction here. The largest part is less or equal than n. Okay. So this part comes here. It's a generating function of partitions with the largest part less or equal than n. So similar things for the under part. Okay, the part under the square also can be treated like this. So this part comes from here. So that's how we get the generating function. I remember that for PhD students in NTU, non-technological university, we have to pass a qualified exam and oral defense. Then you will be the PhD candidate. And on the oral defense, my supervisor asked me how to prove this generating function. And I was too nervous at that time. I replied him, I don't know. But the moment I walk out the classroom, I remember how to prove this kind of things. Okay, so I hope you can remember this proof, how to get the generating function here, if you want to research on the partitions. Okay, and here the this research paper is a very classic paper in our direction, in our field. Okay, so if you want to continue to the partitions issue, you cannot avoid this paper. You have to read it over and over, once again and then again. Okay, and later we will introduce more contents about this paper. Okay. Let's talk about a lot of things about this. And let's say the cranks of partitions. And as we just saw, the ranks can only explain the two congruences of the Ramanujan. So it cannot explain the ones here. If you just calculate some value, you will find that. And Dyson, in that paper, in the same paper, Dyson conjectures that there is another partition statics cranks, which would Ramanujan's three congruences together. Okay, he called the statics cranks. Okay, and in fact, until the 1988, Andrews and Gavin found the cranks, the exact definition of cranks. Okay, and in fact, Gavin first defined the cranks for another partitions called vector partitions. And then Andrews and Gavin together defined the cranks for ordinary partitions successfully. However, this definition is much more complicated than that for ranks. So that's why it spends a lot of time to find the definition of cranks. So let's see how to define the cranks. Yeah. Oh, sorry, the order has some mistake here. The rank of partition defined like this, and the crank of partition defined like this way. So let me give some explanation here. So the mu of pi, the mu of a partition defined like this. We count the times of 1 appear in this partition. For example, we use 4 again. Okay. So for this partition, there's no one here, right? So mu of this, we just use pi, okay, equals to 0. And here, 3 plus 1, there is 1, okay? So the mu here should be 1. And here, 2 plus 2, the mu should be 0. And here, there are 2 of 1, so the mu is 2. And here, the mu is 4, okay? So this mu of pi is just the counting of ones in the partition. And then the lambda pi is the largest part of pi. It's not difficult. And for here, the last part here, the v pi. The v pi is a number of parts larger than mu of pi. So you can see that the definition here is such complicated. Okay, as the number of parts larger than mu of pi. So let's see here for this partition 4, the mu is 0, right? So there's another, only one part, the 4 is larger than the 0, right? So the v here is 1, okay? And here, 3 plus 1, there are 2 parts, right? And all of them are larger than the 1. So here the v should be 2. And here also the v should be 2. And here the mu is 2. So we can see that only this part is greater than 2. So the v here is 1. And here, mu equals to 4. All the parts are smaller than the 4. So the v here is 0. Okay. So then let's see this formula. If mu pi equals to 0, here mu pi equals to 0. So the largest part of pi is the crank. So the crank here is 4. And then for 3 plus 1, the mu is not 0. So it should be the v minus mu. So it'd be 2 minus 1. the crank here is 1. And here the mu is 0, so the last part is the crank. So the crank here is 2. Okay. And then for this, the mu is not 0, so the crank is V minus mu. It should be 1 minus 2 is minus 4, or minus 1, sorry. And for the last part, the crank is V minus mu is minus 4. Okay, so this is a definition of the crank. And we use this symbol, big M of M and N, to denote the number of partitions of N with crank M. And we use this big M of M, S, and N to denote the number of partitions of N with crank M congruent to S. Okay, and Andrews and Gowan proved this congruence, or these identities. This shows that the crank they defined is just a statics conjecture by Dyson. The crank can interpret all the 3 congruences combinatorial. Okay. And let's see another comparison of these two, of rank and crank. The generating function of rank looks like this. We have already saw it, and in fact, it's a mock modular form. And for the generating of crank, it looks like this. We can see that the difference is here is a QQ infinity, and there's also infinity, but here is a summation from n equal to 0 to the infinity. And in fact, the generating function here is modular form. Okay. So that means, in fact, we can use modular form to research on such things. And if we use Q series skill to research this kind of thing, if we got some results, we can try to think about does the result have some meaning in the modular form theory? Okay. And let's see the relations between these two statics, the number of ranks and the number of cranks. Let's see some research result. So the works on the N and NTSN and N of RSN, the difference is here. They congruent to the different number. So Lewis and Santan-Gandia has some results on such things. And for the cranks, also the difference is congruent part. And there's another topic about the crank and rank, or combination of them. There are some results. Andrews and Lewis Garvin, they got some result. Lewis and Santan-Gandia again. Let's see some example. So Lewis proved this kind of things. It's a neat identity of the rank function. And Andrews and Lewis conjectured that for the rank, there is some there are some inequality. And Greenman proved this conjecture by circle method. Okay, So you can see that, in fact, circle method is very useful in such topics. And Chen Songhun, my supervisor, and Mao Yuanrong, my academic brother, provide a Q-series proof of a stronger version for this. In fact, they proved there can also be equality for some condition. Okay. And also for the crank, there is some asymptotic formulas. So Dyson conjectured this asymptotic formula in 1989. So you can see that if you remember, they provide the definition of the crank. The Andrews and Garvin provided the definition in 1988. And then 1 year later, Dyson gave a conjecture about the asymptotic formula about the crank. Okay. And Mao Yuanrong proved that for fixed m, as n goes to infinity, they have this kind of relations. The rank and crank have the same order, and the asymptotic formula looks like this. Okay, but this formula, this result is not the conjecture here. And then Brinkman and Dorsey proved Dyson's conjecture in 2016. Okay. And there are two fundamental inequalities on n of m and n, namely on the ranks function. Chen Songhun and Mao Yuanrong again proved these two fundamental things. If you look at these two inequality and think about it, you will find this one talks about, in fact, for same n, the n of mn is a decreasing function for m, for fixed n. For fixed n, the n of mn is a decreasing function of m. This function gives the result of this. Okay. And for this kind of things, this proved that for fixed m, n of m and n is increasing for n. Okay. In fact, if you think about the definition of the rank, you will think, well, this kind of thing, this result should be right, because if we have a greater or bigger n, there should be more ranks, right? More petitions with same ranks, right? But in fact, the proof is not such easy. And for this part is, in fact, you will find that for a fixed n, the m here, the greater m here, that means your the greater rank is, the less petitions will be. Okay, but here are some exceptions. Okay. So for the ranks and cranks definition and some initial results, we just end here, and let's see the works of Atkin and Swinnerton-Dyer. So let's recall that the n of m, the big N of m n is a number of partitions of n with rank m, and we use this three-parameter function to denote the number of petitions S of n whose rank is congruent to m modulo S. And Dyson's conjecture is like this. So if we want to prove Dyson's conjecture, we just have to prove this kind of thing, right? So how to prove this? We use a generating function to prove them. So let's see the generating function for this. It's just one part of the whole proof, which you use this as an example. The generating function will be like this. Okay, this comes from the Atkin and Swinnerton-Dyer's paper. We got this generating function. In fact, this kind of series is called Lambert series. And we use new definition. We use dissection to prove them. So let's see the definition of dissection first. Let's P of Q denote any power series in Q. Then the T dissection of P is given by this. It's a little bit abstract here. Let's give a very trivial example. We just see the very trivial power series here. Q plus Q squared plus Q cubic plus Q to the power of K plus. So a 3 dissection of P can be like this. So we put the Q to the power of 3K here, and then also put the thing here, but we times the Q here, and here again, we times the Q cubic or Q squared here. So that section, in fact, is just that we put the we put the series together according to its power modular the T here, congruent to different number. For example, if we say this whole part, we will see that every part of this series has an exponent congruent to a modulo 3 congruent to 0, right? The exponent here. And for all the things here has an exponent congruent to 1 modulo 3. And for this, congruent to 2 modulo 3, right? So the dissection is just we put the things, the summation together according to the exponent. Okay. So let's see. If we define a new power series like this, we will write such thing like this. In fact, this is a 5 dissection of P of Q. And we find that the arithmetic properties of AN here can be easily deduced from dissection of P of Q. For example, if we find that P sub 4 of the Q with Q to the power of 4 equals to 0, what we can get as the number, the coefficient here, A of 5n plus 4 equals to 0. Okay, this is the idea from the Atkin and Swinnerton-Dyer's paper. Let's see more detail. So we have the generating function for this. This is the difference of 2 ranks. And the Atkin and Swinnerton-Dyer proved that this part in dissection is 0, which implies this. The A of 5n plus 4 is 0. So how to get the 0? It must be these 2 are equal. Then the minus of them equal to 0. Okay. And in fact, Andrews and Bent rewrote Atkin and Swinnerton-Dyer's proof in chapter 2 of Ramanujan's Lost Notebook, part 3. If you don't want to read this paper, you can just read this modern language. But I recommend you to read this strongly. It's a very classic paper. Okay. And let's see, the 5 dissection of this generating function looks like this. We'll say that for the first line, okay, the power of Q here can be divided by 5. Okay, so in fact, it's congruent to 0 modulo 5. And for the second line, for the square bracket, it's also a generalization of the circle square. It's also a product. So we don't give the definition here. It's also a production. Okay, so let's say the power here. The power here, we can say the exponents congruent to 2 modulo 5. And for the last line, for the last row here, we will see that there's a Q cubic and all the powers here can be divided by 5. So the exponent here is congruent to 3 modulo 5. Okay, so what we got here, the P1 of Q to the power 5 equals to 0. The P sub 4 of Q to the power 5 equals to 0 also. So we can get the A 5n plus 1 equals to 0, and the A of 5n plus 4 equals to 0. And this comes from this, and also this got this. So that's how to get this two identity. Okay. And this is how to find the 5 dissection of this. We have the generating function here. How to get the 5 dissections? We will consider the number series part here, and we use lemma. We can write some number series together like this. And we will take some parameters B1, B2, and B3 carefully to get what we want. And then we will get these two identities. And after get these identities, we will get the results we just saw. Okay. And due to time reason, we don't give other details here. And there are some applications of acting at this. Sorry. And use their method, we can get a lot of results. So Atkin and Hussein obtained formulas on rank difference modulo 11. Okay. And Lanjar and Osborne obtained formulas on rank difference for over partition, another kind of partitions and partition without repeated odd parts. And Mao obtained formulas on rank difference modulo 10, and Chen studied arithmetic properties for Newton's phi functions. And all the papers here in fact, applications of Atkin and Swinnerton-Dyer's method. Okay, so let's introduce some recent works on ranks of partition. So first topic is the rank and crank moments for partition. In fact, the moment comes from possibility theory. In the possibility theory, the moments are studied much more. And here, let's see what's the moment here. For positive integer key, define this is a moment of the rank. We just times t to the power key here. Okay, and it has some kind of like a weight, but in fact it's called the moment, and this is a moment of crank. Okay, and some mathematicians study the relations between even rank and even crank moments. So this is a result from Atkin and Gavin. Okay, and also there are some results about the inequalities between rank and crank moments. So Gavin proved that for the crank moment is greater than the rank moment. If you remember that Renrong have proved this kind of thing. But here we can see that if we times a moment things here, the thing will be like this. The crank is greater than the rank moment. The crank moment is greater than rank moment strictly, but for the even part, okay. And Andrews, Chen, Kim proved that this, okay, from the even to the all the key here. And for the asymptotic, Freeman and another two mathematicians obtain the asymptotic formulas for the even rank and crank moments, and they obtain the asymptotic formulas for moment mk of n and nk of n after 3 years. Okay. And here is another topic about crank. With the identities on cranks, on ranks. And here, suppose that there are 4 identities from the Ramanujan, and the F here, all the F here, in fact, are just generating function of rank. And we just take the different roots of square into the C. Okay, here. So here is it's an identity about the ranks here, and then another 3. Here is another identity. These 3 functions are generating function of ranks, and there is a product. And here for the 3rd entry, it's also about the relations between the ranks modular different integers here, and there is a product. And here for the J, it's also a product. Okay, we just ignore it. And for the last entry, it's modular 4 and 8. Is here. For the 2 generating functions of rank, and here is another generating function of rank, and what we got is a product. Okay, and to this kind of identities inspired us to find the more identities link the rank, the generating of ranks modular different integers. So here, my supervisor and I and Jerry and Lovejoy had a paper got such kind of identity. In fact, here the F is a generating function of rank. And the C here, in fact, is a generating function of crank. Okay, so we find identity link the generating function of rank and crank, and there is a product. Okay, this inspired by the Ramanujan's 4 identity. And in fact, we also get the 3 dissections of ranks modulo 9. Here is 3 dissections. The first line or the power here in the first line congruent to 0 modulo 3. And all the series part here with has a power congruent to 1 with modulo 3. And for the last line, have the power congruent to 2 modulo 3. Okay. And from this dissection, we can get these relations of rank function. And this kind of identity are not didn't appear first in our paper. It has been appeared in Lewis' paper before. Okay. In fact, I use a lemma and use some different identity, take them into the Ramanujan's identity and get some result. For here, f is still the generating functions of rank, and the h has a definition here as just a product. So I found some identities link the generating functions of rank modulo different integers, and the identities have some products here. And the interesting things here are they have the same coefficients here. So it's kind of symmetric identity. Okay. And there's another topic as the total number path function associated to ranks. So let's say the definition, we use the nt of m and k and n denote the total number of paths in the partitions of n with rank congruent to m modulo k. So here we count the total number of paths in the partition. In fact, for me, it's a little bit strange when I saw this definition, because I will not come up with this idea to count the total number of paths in the partitions. But in fact, we find that it's interesting and has a lot of things to study. So Andrews proved the following congruences for the NT functions. Okay, we have this kind of congruences conjectured by Big and proved by Andrews. So the interesting here is that it also has modulus 5 and 7 here. Okay. And Sean Chen proved this kind of result. If we use this to denote the total number of ones in the partitions of N with crank congruent to M modulo K, he proved that lots of congruences for this kind of functions, such as this. And Chen and Mao and Osborne also proved some results of total number of paths function associated to other types of partitions. For example, over partition and then another kind of partition. And there are some results of the identities for NT function. Because that the NT function denotes the total number of paths in the partitions of N with rank congruent to B modulo K. Then applying Atkin and Swinnerton-Dyers method, again, we saw that the applications of Atkin and Swinnerton-Dyers method Mao obtain the 5 dissections of the generating function for this. So in fact, we can see that use the same method, we can try to study different object. For example, here as the NT function. In fact, if you read more article, you'll find that this can be used to the different partitions, and the method in fact is exactly same, and all the different is just the generating functions. And as another applications, more established all the generating functions for this. Okay, so for the J from 0 to 4, we got all the similar things to rank, right? So in fact, what we do is just try to imitate all the things ever did to the ranks. Okay, so maybe we made a conclusion here. So there are many research topics about the rank and the ranks of partition. So first is the equalities. We can try to find the equalities between ranks itself or between ranks themselves. And also we can try to find equalities also involve ranks and ranks together. Okay. And there's another topic, we can try to find the inequalities, maybe for the ranks itself, what we just saw, two fundamental inequalities for the ranks, or we can try to find the inequalities for the rank, or we can try to find the inequalities between ranks and ranks. And there are some results of the identities on generating functions, what we saw just 4 results from the Ramanujan, and we can try to find the more and more similar results. And this part we didn't mention in this talk, just the modularities on generating functions. We can try to study this kind of things from the view of modular form. And the moments we just saw, we can try to aid product part in the series and try to see what we can get. And there's another topic I didn't mention here. If you are interested, you can find them by yourself. And the important things here is, in fact, what we talked about today is just the partitions, right? And if you read the paper, research paper, you'll find that all these things, again, can do it once, can do it for the different partitions. You can do it again. Different type of partition. Like over partition, like some the restriction on the largest part, or some kind of other kind of partition. You can do all the things to over partition. You can try to find the, in fact, already done. You try to find the ranks of the over partition, ranks of the over partition, try to find the congruences, and try to find the equalities, inequalities. And if you find another kind of partition, and you can do it again, find the rank, find the rank, find the congruences, find the inequality, find the equality. So in fact, for this such issue, for the partition issue, you can try to, you can find a lot of things to do. And in fact, since this the topic, the main theme of the summer school is number theory and cryptography. In fact, once I think about how can we apply the partition and related issues to the cryptography. But the thing is that for the generating function, or the function of P, N, and the rank or rank, our function is injective, right? it then has the property like the hash map, as can map different thing, can map A or B to the same different thing, but it's not, in fact, it's not an injective map, right? So what I try is just try to define some like p-adic partition. Try to get some modular thing. Then we can try to use it to cryptography. But I find that, in fact, the definition of the partition is just the summation property. That what I mean is we count the way to add up to n. Even we think about the p-adic thing, the way the count of the way is the number of the way should be the same. So I didn't find the link between the partitions and the cryptography. So maybe you can try if you can apply something from the partitions into cryptography. I think that will be a very interesting part. Okay, so my talk should be end here. Thank you for your time.
Okay, let's give him a big applause. Thank you for completing the lecture, because from this morning, I mentioned a little bit about rank, only give some ideas. And then you can also talk about how to see the rank and crank using, and you talk in details a lot of things about rank and crank, and also related research about that. Okay, so maybe any question? No one? Yeah, because some participants here, I think most of them are new in integer partitions. So yeah, I'm still thinking about your last result with Lovejoy and your supervisor. In 2021 or in IGNT?
Yeah. Right.
Yeah. Because the idea here is so.
In fact,
the idea.
The idea here, how to get this? You get three dissections.
Yes, but I mean, how you define your F1Q and your F2 eta?
Oh, this comes very natural. In fact, if you got three dissections of rank modulo 3, and in fact, Renrong already got a three dissection of rank modulo 3. Here is 9 and here is 3. You just compare the dissections. You will find that there are a lot of same series. You just console them. You will get this. You will get this this such identity.
So basically, the three dissection for CQ.
Yeah. So all the things comes from the dissections.
Okay. And is it possible to find another result from another dissection, maybe? Because that one, I don't know.
In fact, they have tried 5 dissections of rank modulo 10. Yeah. And in fact, we saw this identity is we can prove this by 2 dissection together 2 dissection of ranks modulo 4 and 8, and then we just compare them. We got this identity.
Okay. Yeah, must be a lot of work behind this.
Yeah, a lot of calculation.
The calculation is not that simple. Yeah. Okay, from anyone? Because the important thing is the question related to rank is maybe for different type of partitions. Maybe the idea to build the function, the generative function for the rank or crank will be quite different. So this one, we are still talking about the ordinary partitions, right?
Yeah.
Yeah, from some others. Yeah, okay.
In fact, if you try to deal with other type of partitions, if you find the generating functions similar to the original partition, you will find all the things will be very similar, right?
Yeah. Correct. So there is one question from the chat box.
What does the A key denotes about given by? Oh, I can show you. It's a very complicated thing. But I can show you. Please wait a moment. Let's see. Can you see things here?
Yes. Yeah.
Okay. So let's find the book and chapter 5. Let's say.
Remaining with our time, and you, we discussed this book.
Yeah. Let's see the results here. It's quite complicated, so I just put it here.
That's quite
This
long.
is the result. Let's see how the definition of AN. Here, AN is the summation of this kind of thing. And the S here is called the foot circle. It's another definition, sorry, because it's such complicated. Yeah. Definition of AN is here. And the e to the power of here, the S of H and key is related to the foot circles. Let me see the definition here. Oh, I'm not sure where. I'm sorry, I cannot find the exact definition of S here, but you can see this is the result, and the AK is defined as this. In fact, it's just a series of complex number. S. I forgot where the definition of S here. Sorry.
I think we can find it in this book, right?
Yeah. If you read the whole chapter, you will know the definition.
The definition should be there. Because this book, Apostol, so previously you just mentioned about modular form. First from share, and then the second one is from Canon. I think that one is more advanced compared to this one.
Yeah. The Konos book, right?
Any more questions? So yeah, of course, when you want to learn this kind of stuff, maybe the first thing that you should do is try to strengthen your knowledge about complex analysis.
Yeah.
Because yeah, a lot of definition from there, and we are using a lot of things from there. Okay. No more? Are you sure?
It's okay.
Okay. Yeah, I think, yeah, because I mean, I only share the introduction and also the idea. So I think it's good to see your talk also, because the whole details in your talk. So yeah, that's really help us to understand more about crank and cranks.
Yeah, if you are interested on the partitions, you can find a lot of things to do.
Yep. Yeah, a lot of things to do, but maybe yeah, find a way to solve it is more challenging.
Yeah.
Because sometimes simple question, but how to answer, we need a lot of tools. Okay. So I think that's all. Let's give him a big applause again.
Thank you.